talked a little bit about shape, we talked about the Hoff transform, and we talked about connected component analysis, that process of breaking up a binary mask into individual regions. And then we started talking about how we can describe the shape of those regions, a little bit like image descriptors. We're trying to take a digital fingerprint that somehow encapsulates or characterizes, not an image in this case, but the shape of one of those regions. And we looked at some very basic ways of doing that, what we call the shape factors, things like compactness and so on. We ended up with a short discussion on something called statistical moments, and I introduced to you 1D statistical moments and how they can be considered a more general form of some of the common statistics we calculate about number distributions like the mean, the variance, the skew, the kurtosis, and so on. We're going to see now how we can generalize those 1D moments into 2D moments, and then we'll see that those 2D moments are useful ways of describing shapes, a more sophisticated alternative to these shape factors I introduced last time. Then we'll show how we can incorporate these shape descriptors as little fingerprints of shape into classifiers and start being able to build classifiers that can tell the difference between different kinds of shape. We'll be using the eigenmodels again for that. We'll focus then on some filtering operations called morphological filters and end with a short discussion on chain codes. So I ended up last time talking about these statistical moments in 1D, and we'd looked at moments about zero, but then we also looked at what we call central moments, moments that are calculated about the mean. And we saw in general that we have this formula mu subscript alpha, where alpha is the order of the moment, and this is a 1D central moment equation here. And if we do alpha being 1, then we get the mean. We get alpha being 2, we get the variance, 3 the skew, 4 the kurtosis, and so on. We're going to look now then at the equation for a 2D statistical moment. And just like last time, let's begin by looking at the equation for the moment about 0 rather than the moment about the mean. So this is the equation here for two-dimensional statistical moments about 0. So we write this again m, because it's the one about 0 rather than the mean. And we've got two subscripts here, I and j, which indicate the order of the moment with respect to x and y. You can see the equation is basically the same, except we've got a double summation now over a two-dimensional signal instead of a one-dimensional signal. It's a two-dimensional moment, okay? And obviously the relevance to this is that this two-dimensional signal is your image, okay? So we're computing these things over image quantities. So f of x, y is our usual equation for a function for an image where we've got a function returning a grayscale value for some coordinates x and y. And we're doing a double summation now over all values of x and y across the width and height. But this time, instead of having just x to the power of some of the moment, the order of the moment, we're having x to the I, y to the I, where I and j control the power of the moment. The equation for the 2D central moment is similarly generalized. Remember last time we just took the x and subtracted the mean. Well, now we've got a mean we can calculate in the x and the y direction. We're going to subtract that from the x and the y respectively, and the rest of the equation remains the same. And it's this equation, the 2D equation for a central moment, the moment calculated about the mean, that is useful to us when we reason about moments to describe shape. Just as before, we're going to have this convention where the moment about 0 is going to just return us the 0. So we have this subscript here. If this was 0, 1 or 1, 0, then we just have 0. And mu 0, 0 just by convention is going to equal to 1. But if we have these numbers being of greater order, like 1 or 2 or 3, then these will describe things like the mean in one direction, the variance in another, and so on. And as we get to increasingly high order powers of this moment, we can describe increasingly complex features of a shape. So although it has nothing to do with Fourier analysis and the decomposition of a signal into frequency components, you can think of it, at least at a high level, as a little bit similar. You know, if I perhaps forget about 2D for the moment, imagine we just have a 1D number line. I start talking about the mean, well, that just tells us where the center of the distribution is. I start talking about the variance, which is the order 2 moment, central moment. Then we start talking about the spread about the mean. The skew, we talk about how lopsided the distribution is. And as we move on to the kurtosis, which is the order 4, 5 and 6, we start getting increasingly complex descriptions of the distribution of that signal. So increasingly higher order moments, central moments, give us, describe us different facets of the shape that we're computing. So these moments, each of which gives us a single value, can be combined to produce some quite interesting properties. So, for example, we can calculate the orientation of a shape. Previously, when we talked about taking a region, one of those connected components, and calculating its orientation, we were looking at computing PCA, an eigenmodel over the xy positions, and looking at the angle the principal eigenvector made with the vertical, or one of the principal axes at least. But it turns out that you can calculate the orientation of the shape by just taking the arctangent of this ratio of certain central moments. Okay, we won't go into the proof of that. And another very useful combination of moments is what we call the Hu moments, which were developed by this chap Hu. And it turns out that certain combinations of these central moments give us affine invariant shape descriptors. Who remembers what affine invariant means? What is an affine transform? Right, so an affine transform is a rotation, a scaling, a translation of an image or a shape, let's say. So if we say a descriptor is affine invariant, it means if I take my shape, I rotate it, I scale it up, I shift it around, it's still going to give me the same descriptor if it's an affine invariant descriptor. So these 7 numbers, which can be computed just as simple sums of different combinations of these central moments, will give us these 7 numbers here that we can calculate about a shape. So, for example, to calculate this first number here, we calculate the second order moment in x and the 0th order moment in y, and we add to that the second order moment in y, 0th order moment in x. These are just 2 numbers we calculate via that equation. These sum to give us a single number here, and through this increasingly complex set of summations, we come up with these 7 numbers. These 7 numbers can be considered to be a point in a 7-dimensional space, yeah? Okay, so what we're doing is we're taking our connected component that we maybe think about the plate that we broke up last time, yeah? Each one of those fragments of the plate was a connected component. We want to somehow describe the shape of that region. Well, we take that region and we do that summation over it to compute these different moments, and then we ultimately boil that region down into a point in a 7-dimensional space by calculating these Hu moments. Does that make sense as a pipeline? Okay. Well, we're not going to dwell on the Hu moments because, no, don't panic. You don't have to remember these particular equations for the exam. It's not something I'd be cruel enough to expect, or it'd be rather even useful to remember. You can just look them up in the textbook. But it's interesting that this combination of 2-dimensional moments gives rise to an affine invariant descriptor. And in fact, they can be computed over any image. It doesn't have to even be a binary image or a single connected component. Because that summation is just over a signal f of xy, we can compute it over just a regular grayscale image. So this is taken from one of the course texts, the Gonzalez and Woods Digital Image Processing Handbook. And if you look at this figure here, we've got an image, and this is the original image, this is the half-size image, this is a mirror image, this is rotated 2 degrees, and this is rotated 45 degrees. And these are the 7 components of the Hu moments. And look, the value hardly changes for each of those elements of the Hu moments as we perform those operations, which shows it to be affine invariant. Yeah? So these things are particularly useful for things like character recognition, and they're used extensively in optical character recognition applications. So now that we've got a way of calculating an affine invariant descriptor, that point in 7-dimensional space from a shape, we can start looking at how we might apply these things for shape classification. So we call these things shape descriptors, and just like descriptors we were calculating for images, we have these 2 desirable properties of shape descriptors, in that we'd like them to be discriminative, yeah, we'd like them to tell one shape from another, but we'd also like them to be compact. Okay, and the Hu moments serve these properties very well. They're only 7-dimensional and they're discriminative, and have this useful property as well that they're affine invariant. So, thinking back to our plate example then, we had this binary mask that we extracted from our conveyor belt as the plate went along. We were breaking it up, iterating through the connected components in here, and we were calculating a shape descriptor. And we were just looking at shape factors, particularly compactness for this plate example. But actually, we could equally have calculated some of these statistical moments and calculated the Hugh moments for that shape, right? Okay, so these are both examples of region-based shape descriptors. And next week, on Tuesday, we'll be looking at a contour-based shape descriptor that calculates descriptors from the outline of the region rather than the binary mask of it. But coming back to that shape classification task, then we have a very similar pipeline to our image visual search system. We have an image here. Okay, this has got a shape in it, a binary mask here of this arch. We're going to calculate the Hugh moments using those equations to get a point in a 7-dimensional space, and then we would assume that similar shapes would map to similar points within that 7-dimensional space, right? And we'd also assume, because the Hugh moments are affine invariant, that I could take this shape, rotate it, scale it up, shift it around in its image, and we'd still end up at pretty much the same point in that 7-dimensional space. Everyone following that? Okay, so we're taking a fingerprint, digital fingerprint of that shape. So, much as similar shapes would match to similar points in that space, different shapes would map to different points within that, different regions of that 7-dimensional space. So if we had, for example, some circles, some crosses, some fish shapes, okay, they would all map to different regions of that space. And then imagine that I went and then drew a shape. I could then calculate the Hugh moments from that shape, figure out where it is in the space, and then measure the distance between that query shape that I've just drawn with the distributions for each of these clusters of shapes that I'd seen during training. And that would give me the basis for creating a shape classifier. Does that make sense? So these crosses here indicate the models that I've built from different classes of shapes. In this case, I've got 4 models here, one for each kind of shape. I've then constructed those models using some technique. How might I build those models, do you think? Yeah, I could just calculate their average location in this space. So that would be the average Hugh moment. So the 7 numbers, the 7-dimensional vector, that's the average of all of the points here corresponding to crosses. That would give me that. You know, similarly, if I do that for the fish, the arches, the circles, that would give me 4 models. What would be a better way of calculating that model? Eigenmodel? Yeah, absolutely. That's right. Because we've seen previously, at least 2 times now on this course, that it would be better to model not only the center of these distributions, but also the shape of those distributions as well. Yeah? So an eigenmodel gives us that. It gives us a mean and a covariance. And that means when we go and build those eigenmodels for each of those 4 classes, we've got a convenient way to measure the distance between that query and each of those 4 statistical distributions. What is the name of that distance? Mahalanobis distance, yeah, which is the distance in standard deviations of that point for each of those 4 models. Yeah? Then obviously the closest distance, the shortest distance is the winner. So in this case it would be the fish. Yeah? Does that make sense? So you see what we've done there. We've taken an image, we've extracted a binary mask from that image that describes the shape of interest, in this case, you know, the arch or the fish or whatever, and then we've then computed the Hugh moments using those 2D statistical moments to get that shape boiled down to just a point in a high-dimensional space, and then we've built models, statistical models, the eigenmodels, for each of those classes of shape as a training process, and then at test time, we've evaluated how close a test shape is, having gone through a similar process, to each of those 4 eigenmodels. So here are our eigenmodels. And then, yeah, we could use something like a confusion matrix to evaluate the performance of that system, right? We could even use a different classifier. We could use an SVM, but we don't, as I said, cover those in detail on this course. So, here's an exam-style question. You win a military contract to design an air defense system. A camera will watch the sky to decide which kind of plane is flying in the sky. How will you build that system? let's assume that you're working on a system in a country that's not the UK that has lovely blue sky and it's just pure blue, the sky, okay? What would be the first thing you do to extract a shape descriptor from those images of planes? Yeah, so what's the objective here? The objective is to get a binary mask of that shape. Right, where else on this course have we met a sky classification technique? Well, let's focus on the question of ours. I'll come back to your question. How would we extract a binary mask from a shape against a blue background? Yeah, absolutely, thank you. Build an eigenmodel of the distinctively coloured background, the blue background. Yeah, I asked basically the same question last week when we talked about the blue conveyor belt. Yeah, okay. We build the eigenmodel out of, a shot of the blue sky, just with no planes in it. Okay, we build that statistical distribution, that eigenmodel in RGB space, and then at test time, when we're presented with one of these images, we're going to go through every single pixel in this image and measure the Mahalanobis distance of that pixel in RGB space to the eigenmodel that we've built of the blue sky. Yeah, and then that's going to allow us. We're going to threshold then on that distance, and pixels that are quite close to that eigenmodel, we're going to consider to be sky. Anything that's beyond a certain threshold distance away, certain Mahalanobis distance away, is going to be considered to be the plane. That will give us a binary mask then of that plane. Yeah? Everyone happy with that? Okay, and then once we've got that binary mask of that plane, then what are we going to do to get our shape descriptor? What sort of shape descriptor do you think we should use? What would be desirable properties of a shape descriptor in this scenario, where planes could be at any distance from us, flying in any orientation or anywhere in the sky? It would be nice to have an affine invariant descriptor. Which affine invariant descriptor have we met on this course so far? Hue moments a moment ago, okay? So we would like to calculate the Hue moments then of that binary mask, yeah? That will enable us to extract a point in our 7-dimensional space for our plane, yeah? Now, if we wanted to build up a classifier, for example, of MiG, that would tell the difference between MiGs and stealth bombers, 2 types of plane, then how would we build that classifier? What will be an important thing to do when we're trying to train that classifier? We need to collect some training data, yeah? So what we probably do is go out and capture a whole bunch of images of MiGs against the sky, a whole bunch of images of stealth bombers against the sky, extract the binary mask for all of them using that technique that we've just been through, and then extract the Hue moments for all of them. So that's going to give us a distribution in our 7-dimensional space for MiG bombers, and a distribution in that same 7-dimensional space for the stealth bombers, okay? And then we're going to build eigenmodels for each of those classes. So we're going to build an eigenmodel for each class. Yeah? That would then train our system. So then if we needed to, having trained our system, we needed to figure out which plane was in a particular photo of the sky. Let's say it's this photo here, which is not going to be part of our training set, remember? Okay? We would then perform that same eigenmodel thresholding process to extract the binary mask from the background, compute the Hue moments, and then we would then have a point for this image in our 7-dimensional space. We would then measure how far that point is from each of our 2 models by calculating its Mahalanobis distance, and then we would look at which Mahalanobis distance was lower, and that would give us a decision on whether it was a MiG or a stealth bomber. Does everyone follow that? Yeah? So I think your question was around what would you do if the planes were different colours?
No,
yeah.
So there's colour information in the plane, other than just the outline shape.
So in this example, I'm sort of simplifying the problem by sort of saying you've got a dark coloured plane, or at least you've got a plane against a distinctively coloured background, which is blue. In reality, maybe you're going to have some colour of the plane that's the same as the colour of the sky, and it's a bit more complex than that. But right now, we're just looking at kind of a very simple scenario. Yeah. All right, so this was the solution then. So you'd separate the plane from the blue sky using this color classifier. You calculate a shape descriptor from that region. You then perform a supervised classification using an eigenmodel. So you end up then with this sort of scenario. You've got multiple classes of object against the sky, and you can classify which one it is. And then you would perhaps evaluate the performance of your system using something like a confusion matrix. Yeah? Okay. So, let me see if I can give you a demo of something. Depends very much on whether there's a lead kicking around here. Oops, my timetable. It's a timetable that reminds me that this Friday we have a lecture at 2 o'clock as well. Okay, so. All right. Let's give me a moment to switch over to MATLAB and we'll do this demo. We've got some sort of chronic problem here with the... Okay, so I just want to show you a quick demo of something I produced in MATLAB. So to build this demo, this is a shape classification demo using those examples from the slides a minute ago. So some time ago when I was more enthusiastic than I am now, I sat there and drew a whole bunch of shapes, of arches, circles, crosses. As you can see, there's quite a few in here. We've got some fish in there, some squares, triangles, okay? And I've got a bit of code here which you'll get to play around with in the lab, and I'll talk a bit more about this code as well next time, which basically will do exactly what I've just talked through. It will go through and load those images up and calculate hue moments from them and build, in this case, 6 different eigenmodels, one for each class of shape. And then the idea is that you draw a shape, and when it comes up with a prompt, so at the moment it's just calculating the hue moments for those. Right, I'm going to then draw a shape. What shall I draw? Which of those classes of shapes shall I draw? Fish, always the fish, every year it's the fish. Thank you for the description. I should just change this code to just return fish. Right. Right, now. It's a bit anticlimactic, but let's have a look here. So what's happened here? So you can see you drew a fish. So why have we come to this conclusion? Well, what's happened, and we'll step through the code next lecture. This is more of a kind of a preview. Is the system has loaded up those different sets of images. It's computed the descriptors from all of them. It's built the 6 eigenmodels, and then I just drew a fish. It then calculates the hue moment descriptor for that fish, for that query, and then measures the Mahalanobis distance between that query and each of those models. And these here are the Mahalanobis distances. So you can see that the lowest one here is for the second class, which was the fish. But the second lowest Mahalanobis distance was this one here, or more, it's a little bit like a cross, maybe a little bit like a triangle. You can see why it might think that from the tail, but it's very dissimilar to a square, for example. Okay, so you can see what's going on there. They are not actually probabilities. I shouldn't say probabilities, they're likelihoods, because they don't sum to 1. Say that. Okay. Right. So yeah, we'll look at that code in a bit more detail next time. In fact, in some detail next time. I haven't looked at it at all yet. But feel free to play around with it if you like. It's in the Solo. Okay. Right, has anyone got any questions there about the hue moments and building a shape descriptor? Yeah. Yeah. Like so right now we just looked at two simple kinds of shape descriptor. We've looked at shape factors. So shape factor you can consider to be like a one-dimensional shape descriptor. So something like compactness, which if you remember was perimeter over area, basically. Yeah, perimeter over area squared. That's like a one-dimensional way of representing a shape. It gives you a number for a given shape. The hue moments is a way of getting 7 numbers for a given shape. So I could have built these eigenmodels in one-dimensional space and used compactness, but it would have given me a really bad descriptor. And as we'll see in the next hour, as in the first hour of the lecture on Tuesday, there's an even more powerful way of representing shape we call Fourier descriptor. That's what we're going to spend next hour talking about. And in fact, you can control how many dimensions that descriptor has. No. So the guy that came up with these hue descriptors just designed these seven combinations of the central 2D central moments. So they're just defined as it's a 7-dimensional space. Any other questions? Yeah. Well, you get a less discriminative descriptor. So it's the 7-dimensional descriptor that is affine invariant. So yes. Okay, so let's move on to a related topic, and that is about how we can pre-process this binary mask to clean it up a little bit. So right now we've assumed that it's possible to extract a binary mask cleanly from the background. We talked about this artificial scenario where we have, a really blue sky in the UK or like a blue conveyor belt. And we've used this kind of simple thresholding operation to using an eigenmodel to extract that binary mask from the background. It's not often the case that we can get a binary mask that's quite as clean as that. And in fact, normally, if we're extracting a binary mask, we'll end up getting not only a binary mask for the object, but also quite a lot of speckly noise as well in that mask. And it's desirable to remove that noise before we start trying to iterate through the connected components, because otherwise we'll just have hundreds, or maybe computing moments, in which case they just add inaccuracy to it. So, for example, if we were taking a scan of a fingerprint using one of these optical scanners, which ultimately shines very bright light on the fingerprint and then thresholds the image, we'd end up getting an image a little bit like this that we need to clean up before we started processing the image itself for example, shape recognition for fingerprint recognition. Well, one way that we can perform this filtering is using something called a morphological filter, which is a very complex sounding name for a very simple idea. Morphological filters, well, there's two of them. There's the erosion operator and the dilation operator. So let's look first of all at the erosion operator and how it can help. So remember, the objective here is to remove some of these spurious additional kind of speckles in the image here. In this case, these white speckles from the background. And the property we're going to use to remove those speckles is the fact that they occur in isolation from the larger structures in the image that we're more interested in, okay, like the fingerprint in that previous example. So, in other words, we'd like to remove these speckles here, and actually we'd also like to remove the black speckles that are making artificial holes in the image as well. But let's look first of all at this process of erosion. What we're going to do is very similar to convolution. We're going to establish a window over the image, and we're going to slide that window across the image, making decisions as we go in order to construct a new output image. So we're going to create an image that is the same size as this input image, and we're going to sweep this window over the entire image, and at every position, every pixel we center this window on, we're going to count up how many pixels are on and off within that window. Okay? Now, because we're doing a counting operation here, this is not a linear operation. So this is, although it looks like a convolution because we're taking a window and sweeping it over the image, this is not a convolution, it's not a linear operation, right? So it can't be implemented with convolution and frequency domain and all that sort of stuff. We have to actually just code it as a loop, okay? So what we're going to do is go through the image with this structuring element, as it's called, because we like terminology in computer vision. We don't call it a window when we're talking about morphological operation. We call it a structuring element, but it's just a window, okay? And then what we do is we sweep that window over, and at every location, we're counting the number of pixels that are on within that window. And you can see that when the window is centered here, we're only going to count one pixel as being on in this location. But when the window is centered somewhere else, like here, for example, in the image, we're going to count more than one. Yeah. So we pick a certain threshold that we're happy with, like 1 or 2, and we say if the number of on let's say 2. If the number of on pixels within that structuring element is greater than some n, let's say 2, then we're going to output a 1 at the corresponding position in our output image. Otherwise, as is the case here, we're going to output a 0. Okay, and we're going to move through the entire image doing this until we get to the end. And then what's going to happen is we will copy across all of the kind of gross structure in the image, but not copy across the set pixels that are occurring in isolation in the image. And we refer to the output of this operation as an eroded binary mask. The actual, the actual visual effect of this is to remove not only speckle noise, but also to slightly shrink the coarse grain object that's in the image. So it will reduce very slightly in size. It will be eroded in its footprint in the image, but we will also lose that artificial kind of positive speckle noise that we see there in the image. Notice that we've still retained the unwanted negative speckle noise there, the 0, the spurious 0 in the middle of the shape. Everyone happy with that? So the opposite operation, if you like, of the morphological operators is what we call the dilation operator. And the dilation operator works exactly the same, except this time we're counting the number of off pixels in the element, and we say if that number is greater than some threshold, then the output will be off, otherwise it's on. So in this case, when we get to, for example, here in our image, we're going to count only one off pixel. Okay, so it won't be greater than that threshold, let's say it's 2. So the output will therefore be on. So it will be like kind of filled in that hole. But other expanses of zeros will be retained as zeros. Does that make sense? Yeah? So having performed this dilation operation, the net effect is that any of these spurious black holes, the negative noise in the image will have been filled in, but the image will have grown, the region that's coherent in the image, the connected component, will have grown slightly in size. So what we've seen here then in these two examples is we've taken a noisy image here, we've eroded it, which removed the positive speckle noise, and we've then dilated it, which has filled in the negative speckle noise. And the result of the erosion was to slightly reduce the size of the object, but the dilation then restored the size of the object. Yeah? So that combination then of erosion followed by dilation has cleaned up the image. But notice that they're not, although they're conceptually the opposite operators, they're not the inverse of one another. Yeah? Because eroding the object and then dilating it with its conceptual opposite operator, in other words, hasn't restored the original image, it's given us something else, which in this case is the cleaned up image. Okay, so they're conceptually the opposite, but they're not the inverse of one another. Okay, so this erosion followed by dilation is what we call a binary opening, and the dilation followed by an erosion is what we call a binary closure. So opening and closure are just combinations of these two basic morphological operators, and these have the the effect of cleaning up the image. So in this case here, we've taken our fingerprint image, this is the one I showed you at the beginning, and we performed that erosion operator on the image, and that has removed the speckle noise, but it's also shrunk the fingerprint a little bit, yeah, it's eroded it. But then when I perform the dilation, it's then restored the original footprint of that fingerprint. Footprint of that fingerprint. That's not a good way of saying it. The original shape of that fingerprint, but it has not restored the speckle noise. Yeah. So that was an example of opening. And then let's have a look here at the closure. In the case of closure here, what we've done is we've taken that image, and you'll notice that this is the output actually of the opening process. It's got these little fragments here between the ridges of the fingerprints, but within each ridge of the fingerprint, sorry. And then what we've done here is dilated this image, which has then grown the structure so that these small gaps have, for the most part, been closed up. And then we've eroded the image to restore the approximate number of pixels that were on there in the image, but in fact, these gaps have been closed up here. And that can be quite useful if we were doing something like optical character recognition, for example. What we might do is we might take a page of text that we've scanned, which is ostensibly black and white image. We could threshold it so that it's truly a binary mask. Okay, so we could threshold on the grayscale level, for example, just to simply isolate the letters from the page. And then what we'd probably find is the letters on the page, we had this speckle noise around them. We also had some small breaks in the letter where the threshold wasn't quite right. We'd use something like a binary opening and closure to clean up that text for processing. Does that make sense? Yeah. Well, what do you mean by edge pixels, sorry? Yeah. Yeah. Oh, you mean like the boundary conditions? Yeah. Well, you can come up with some heuristics there, or you can just say, let's not process them, let's just copy them directly over. But yeah, it has the similar issue with boundary conditions as you get with convolution, so there are multiple strategies to handle it. Yeah. So another really useful combination of these morphological operators is to perform a crude kind of edge detection on the binary mask. So, for example, if I were to take this binary mask and I were to erode it and take that result, and then if I were to take this original binary mask and dilate it and take that result, and then difference those two intermediate results, then I get an image that looks like this, which is the difference between the dilated image and the eroded image, which gives me a map of all the boundary pixels on that object. So remember, when we were talking about like shape factors at the beginning of this shape representation section of the course, we were talking about how we might want to count up the number of pixels in the perimeter of a shape, and also count up the number of pixels in the area of the shape. Well, counting up the number of pixels in the, calculating the area of this shape is easy. We count up the number of set pixels. If we want to count the number of pixels that exist on its perimeter, then we could just use this operation and then just, again, count the number of set pixels. So, okay, so for today then, we've looked at two things. We've looked at a shape descriptor for regions called the hue moments, and we've looked at how that can be built up into a classifier, and we've also looked at a way of cleaning up the binary mask before we perform this iteration through the connected components in order to simplify a problem. The last thing I want to show you in the last 10 minutes of today is another kind of shape descriptor. But this shape descriptor, instead of being calculated from the region of the binary mask, is calculated from just the contour, the outline of a shape. And we're going to see that, in fact, this simple kind of shape descriptor that we call the chain code is just has its drawbacks. It's a very basic form of contour shape descriptor. But in the next hour, on Tuesday, we're going to look at the Fourier descriptor, which is a much more sophisticated and state-of-the-art form of shape descriptor that's computable from the contour of a region. So this chain code is actually arguably the first shape descriptor that we started working with in computation back in the 80s, sometimes called the Freeman code. There's Bill Freeman who created it. The idea is to represent the contour or path around the perimeter of a shape by a sequence of moves that are coded using the points of the compass. So we can talk about, just like with connected components, either a 4-connected or an 8-connected chain code, which would consider whether we just move in north, south, east, west directions, or whether we move in also northeast, southeast, northwest, southwest directions as well. So if I had a shape then, as I iterate around the contour of the shape, I take steps to move around the boundary of my shape, and each one of those steps will be a move in the north, northeast, north, whatever point of the compass direction, and we're going to encode each of those directions with a number. And that string of numbers, the moves we've made to walk around the perimeter of the shape, is what we call a chain code. Okay. So, for example, if I had this shape here, okay, what I would do is I would walk around the shape in some equidistant steps, and every move that I made I would encode with a number representing the direction that I've moved in order to encode the perimeter of the shape. So these can also be used for compression as well. So if I were to move around the shape and take multiple steps, so maybe I'm working with quite a large shape. So if I walk down the side of the shape, I might take 100 steps in the south direction. I could just encode that by just saying 100 south moves rather than 100 individual codings of the direction south. So you can produce quite compact descriptors in this way, which, as we recall, is an important property of descriptors. So if I were to ask you, do you think a chain code could represent all possible shapes? The code, yeah, so that's right, absolutely. So the chain, you're jumping ahead a bit here, so let's ask the questions. Can chain codes represent all possible shapes? Yes. Yeah? But, if it's a ring, well, that's fine. I can encode a ring by just stepping around the perimeter of the ring, that's fine. I see. Okay, so yes, so you can produce a chain code for the for every contour in the shape, yeah. But we're just simplifying the description here, just the exterior perimeter of the shape. Yes, they can. Right. Are they invariant to translation? Well, hopefully you see that they are, because it doesn't matter where that shape is on the page. The same sequence will walk me around its perimeter regardless of where it is, on the page or in the image, if you like. But as soon as I rotate or scale up that shape, it's going to change the coding that I get for that shape, right? But yeah, as was just pointed out, one of the disadvantages in its naive presentation here is that it's sensitive to where you start coding the shape from, right? So the same chain code, there are multiple chain codes under this definition that will give me the same shape. If I start here, the code starts 66655. If I start here, the code would start 076665, and so on. Okay. So what we'd like to do is figure out a way of determining where the right place is to start coding our chain code from on the shape. And this is where we end up with this we call start point invariant chain codes. And what we're looking at is looking at the string that we get. CC here refers to chain code. We look at the string that we get walking around the perimeter of the shape to generate that chain code, and we notice that just by rotating this string, so for example taking this 2, putting it to the start, and then you've got another chain code, all the sort of string rotations of this chain code give us the same shape. So we need to figure out which of these string rotations is the correct or best one. So one way that we can do that is just by differencing adjacent points, adjacent moves in the chain code, using a scheme where we might say, well, look, if we've got a 1 here and then moves to a 0, okay, then that is just one step. You're going to go anti-clockwise. So that is 1, 2, 3 moves around our compass to get to that point. So we're going to write 3. Then we go from 0 to 1. That's just one move, so we're going to write 1. Then we're going from 1 to 0 again, So that's 3 moves, 1, 2, 3. And we build up this thing called a first difference string, which is a way of calculating. Well, it's basically it's like a meta descriptor for this descriptor. It's like a descriptor built from this string. Yeah. And if we were to interpret that as an integer number, one way of giving ourselves a reference point as to which chain code we should use is to look at all rotations of this chain code and all their integers that we generate for their first difference, and figure out, either the largest first difference or the smallest first difference, whatever we choose our convention to be, and take that to be the chain code that we use. And that removes this unfortunate property of the naive definition of chain codes, which is that it's sensitive to its start point. Does that make sense? So these sorts of simple path coding techniques are used in things still like, like in Firefox or whatever browser, where you make little gestures on the screen and it recognizes gestures. Usually those gestures are just quantized into several moves, turned into a string, and just some simple string comparisons used to detect gestures, for example. So for simple gesture recognition, these chain codes kind of work quite well. As a practical shape recognition tool, today in computer vision, honestly, they're not used very much, but I introduced them just now because they're a useful intermediate step in getting to them. So, for example, to compute Fourier descriptors, that we'll talk about in the next lecture, it's sometimes convenient to take your image and convert it into a chain code prior to processing it into a Fourier descriptor. And in fact, you'll see in the code that I supply in the lab code that that's exactly what I do. So the basic idea then of creating these start point invariant chain codes is to create basically try every rotation of the chain code and find the smallest first difference. But notice that this is still, it is not the same as rotational invariance, right? Okay, if I rotate the shape itself on the page or in the image, I end up with a different chain code. Okay then, so in this hour, we've looked at several things. We've looked at the generalization of the equation for 1D moments to 2D, and we've used those 2D moments to represent shape using the Hue moments to create an affine invariant shape descriptor that then we showed could be used in a shape recognition system by combining it with this idea of supervised classification and eigenmodels. We've looked at some basic morphological filtering operations like erosion, dilation, and their combinations, which are opening and closure, in order to clean up a binary mask before applying such processing. And we've also looked at a simple kind of shape descriptor that's based not on the region, but on the contour of the shape, and that is the chain code. And next time we'll look at the Fourier descriptor, which is something we tend to use a lot more in practice. If you need to read more about this, I encourage you to look into the course text for morphological operators and shape moments, which is the Snake book. Okay, great. Thank you very much, and I'll see you on Tuesday.
Hey guys, is anyone in here in LSE computer vision?